Hello, and welcome to another enthralling episode of Science. My name is Dominic Bussey. You may remember me from such poorly orchestrated presentations as Why We Need Chemists and 2,4-Dinatural Phenylhydrazine. Today I'd like to discuss with you MO theory. The topics that we'll briefly cover will be what is MO theory, MO versus valence bond, bonding, bond order, and some energy diagrams. What is MO theory? MO theory helps us explain molecular bonding. It also explains some of the magnetic properties that are attributed to particular molecules. And it can also help with the determination of bond orders. It's not real, it's just a tool that we use, an idea, so that we can visualize what's happening with bonding between molecules. So why do we need MO? We've already got valence bond. Does a pretty good job of letting us know what's going on in the bonding between molecules. So here I have collected some of the negatives and positives of both of the two theories. So MO versus valence bond. MO was created by Frederick Hund, Robert S. Milligan, and later on John Leonard Jones and John C. Slater. Valence bond theory, its founders were G. N. Lewis, Walter Heiter, Schrödinger, and Linus Pauling. Now, valence bond theory is very simple in comparison to MO, and it does help explain the shapes that we get from the molecular orbitals during bonding. And it's much easier to visualize. However, the complexity of MO theory means that it can give us more information and be more accurate than valence bond theory. And it also helps explain some of the bonds that VB cannot, such as magnetic behavior. Down here on the bottom is a Lewis structure, which is how you would display valence bond. And over on this side is a MO diagram. So let's talk about the bonding in the s orbital. Here, this hydrogen is joined to this hydrogen, and together the overlap creates what is known as a sigma bond. This sigma bond has an area where the electrons could be delocalized around both nuclei. This is called positive interference. Again, we can have negative interference. So the positive and negatives join to make what is called antibonding, or sigma star bonding. There is a gap, a nodal space in between the two nuclei that repel each other, and there's little to no chance of an electron being in this central area. If there is bonding, there must be some form of antibonding. Here I have drawn two hydrogen ions, and on this MO diagram I have put in the electrons and filled up all of the spaces. This is the bonding, and this is the antibonding. Now this can't work because the bond order, which is half of the bonding minus the antibonding, equals 0, which is impossible. So we'll remove some of these electrons . Now, each hydrogen has put in a single electron, which has filled the lower energy sigma bond, and this is possible. So let's do the bond order for this. So half of the bonding electrons minus the anti-bonding electrons. Half of 2 is 1. as we have a positive number, this is possible. So bond order, half of the bonding electrons minus the anti-bonding electrons. Things get a little more difficult as we move into the p shells, px, py and pz. On the top here I've displayed the anti-bonding for one of the p orbitals, and on the bottom the sigma bonding. The deconstructive interference means that the nuclei push each other apart, causing a gap, as can be seen in the previous anti-bonding diagram. We also have a nodal space between the two. Down here, the positive and the positive combine to make this larger area of delocalized electron, and the same with the negative. We also have a gap right through the center. Okay, that's the end from me. Thank you for watching. If you have any further questions, please send a blank sign check in a stamped self-addressed envelope to PO Box NOTREAL, and we will endeavour to get back to you as soon as possible.